In this final video on pulleys, we're going to look at the same problem I just got through working in the video part 2, but we're going to consider it from a single free body diagram perspective. So you remember in the last video we decided this was going to be X and Y, and by the rule of the gun this was X and Y, and this was X and Y. I want to make this a single object. If this object here moves this direction, then this mass moves up, this mass moves down. So I could treat this like it's just one big single mass. And it looks kind of like an amoeba from biology. So I can think about it as if I just kind of straighten that out so that my X, instead of going in different directions, lied along the horizontal, then this structure would look something like this. A single horizontal, and I'd have this block. It's 5 kilograms, a 3 kilogram, and a 12 kilogram block. And this would be X, and this would be Y. In the positive X direction was the weight for block C. Remember, we call this one C, this one B, and this one A. In this direction, the weight's down, which is in the minus X. So in this axis, that would be that away. I'm sorry, this was A. That's A. The weight of B is down like this. And there's a normal force like this. And if you had friction, then I could deal with friction as well. But this is a frictionless table. And so now I'm working this single diagram rather than the 3 separate free body diagrams that I worked before when I broke this into different free bodies and dealt with these strings as external. The advantage is that the strings are completely eliminated. They become internal forces. And Newton's law says the sum of the external forces is equal to mass times acceleration. If I write the free body, take the free body diagram and write Newton's law for this problem, in the X direction I get sum of the forces in X is equal to the mass, and the mass in this case is MA plus MB plus MC AX. And by the way, there's also over here a Y equation. Sum of the forces in Y is MA plus MB plus MC A sub Y. Running out of paper on the side of the board. For the forces in the X direction, I have 2. I have W sub C, which is in the positive X, which would be MC G. And then over here I have MA G. And that gives me AX is MC minus MA over MA plus MB plus MC, all of that times G. And I get exactly the same thing that I got with the other method, but I've just avoided a whole lot of algebra by choosing your free body diagram wisely can greatly simplify your mathematics. Now, I warn you of a couple things. When you do things like this, combining it, there's a lot of in-between steps that have disappeared. That's great, speeds you up. But its downside in an academic environment is that your instructor can only grade what they see on your paper. They can't grade what you may have thought in your brain. So when you're doing those in between steps and you're putting it on paper, that's things that you can get partial credit for. When you go straight to here, if you draw this wrong, then you don't have very much that's right to get partial credit. So in the real world, when you're trying to, and you've got a lot of experience and practice, this is really useful, and it certainly is useful for getting to the conceptual idea of what's important. But it does have the drawback that you can lose a lot of partial credit if you're just turning something in rather than having a discussion, for instance, with your boss or with your instructor, where if you miss something up, they can ask you a question and you can respond and find your mistakes. Okay, again, we can put the numbers in, and we did already, so I'm not going to do that here. And notice that you can check units again. Mass over mass cancels, so this is just the units of g, and the units of g are the units of an acceleration. In the SI system, that's meters per second squared. Okay, I will talk to you in another video.